Welcome to EE World. I'm Martin Rowe. At the 2022 International Microwave Symposium in Denver, Colorado, we visited the pSemi booth, where David Watling gave us a demonstration of the company's beam steering ICs. Beam steering, of course, is a very important part of 5G, used to concentrate signals from the base station to the user and also from the user to the base station. David's going to show us an antenna module made by the parent company, Murata, working with the beam steering ICs by pSemi. We've got here a patch antenna that has got a 4x4 pattern. And why don't you explain what some of your devices are doing in terms of driving that antenna?
Okay, so the antenna module is a LTCC designed and manufactured by Murata, and so they provide the module, and we provide the silicon that fits inside under the white part of the ceramic, the recess under the ceramic, under which we fit 4 beamformer ICs and an up-down converter. Each patch antenna, so the dark spot here is a patch antenna. Okay, the patch antenna is driven from 2 feeds, so horizontal and vertical. Each channel has 512 preset beam directions, or phase settings.
Okay. So you're changing the phase to get the beams to steer.
That's correct. So you can preset all the different phases to give you different beam directions. Okay, and those are all preloaded at the beginning, which is thousands of registers loaded up at the beginning, which means that you can run this during operation. You can run this at very, very high switching speed, so you can steer the beam in much less than the 500 nanoseconds required for the 3GPP spec.
Okay. Now you also feeding horizontal and vertical polarizations into each of the antennas, so that your device then handles both.
That is correct.
So and how many devices, or how many beams does each device support?
So each device supports 4 horizontal and 4 vertical. So each device supports 8 channels. They're all independent RF channels, TX and RX.
Okay. And you've got over here a setup that you've been using to measure the beam that's been as you're steering it. And you've got a video over here that's showing the measurement of the beam.
Yes, that's correct. So the gimbal, when it's moving, we can use that to slowly build up the beam shape. Okay. So you've got one of these patch antennas down there, I can see. Yes, we have the same as the one that was in my hand. Okay.
And the receiver then is up here.
That is correct.
Okay.
Okay. So each 3D shape takes, unfortunately, about half an hour to build up, so we can't really demonstrate that live.
Of course.
All right.
Okay.
But what we have on the screen here is where I've put together a video of 5 beam patterns in 5 different directions, and I've put them together into a video just to show what the real beam patterns look like.
Okay. And you've got above that, you've got a photo here of the 4x4 patch antenna, such as what we just saw, but you've also got an 8x8 using 4 of those.
That's correct. So the 8x8 and even 16x16 is handled simply by device addressing, and it's just very scalable.
Okay.
Very scalable solution.
And what are these measurements that you're showing over here?
Okay, so this is EVM measurements. So we're showing the linearity and the performance. And along the bottom, of course, we have to know what the output power is. Now, in order to know the output power, we need to calibrate very carefully the air gap within the chamber. So if we go back to the chamber, let me show you. So the air gap from the beamformer itself up to the horn antenna and through up to the analyzer that we have, so that the losses have to be very accurately calibrated. There's a long procedure. It takes a couple of hours, all written down and available to the public if needed.
Okay.
This is how to get a very accurate x-axis on our sweep here.